Hi guys, this is going to be our lecture on heating the atmosphere, which is the first lecture of the Part 3 lecture series. I will be back next week. This week I am currently on my mini-moon, so tied the knot. Thanks for me. So yeah, heating the atmosphere. So this is the beginning of the 3 lectures on meteorology that we're going to have. This one we're really talking about how the atmosphere is warmed and what that affects. So let's review what the Earth is. As we know, the Earth is round. It's slightly tilted, about 20 degrees or so. We have day and night due to its revolution, the amount that it spins on its own, and even though it is spinning, it also is revolving around the sun. Okay. Characteristics of the Earth. We have a variation in biomes. We have continents, soil, land, geology. We have the lithosphere, the asthenosphere. We have the hydrosphere, which is the oceans, seas, water as a liquid. Oceanography is a science. We have the air we breathe, which makes up the atmosphere. And this is where we're going to find gas molecules. This is where we're going to see our atmosphere. This is where we're going to see the meteorology as a science come in. And so the lithosphere, the hydrosphere, and the atmosphere all make up the biosphere, and it's life that exists in the biosphere. And this is something that we have learned and which we express as the geosphere. So the atmosphere. We've already learned a little bit about the geosphere, or geology. We've learned a little bit about oceans. We've learned a little bit about how water affects landscape, and we've learned some about things that happen on our planet, such as earthquakes, subductions, tsunamis. We know that there's a water cycle, and this is the other half of the water cycle in some ways. We know that there is mountains both under the water and on land. We know about volcanoes, magma flows, pyroclastics, density currents, ash, and how that affects us, and how it's little pieces of rock and glass, and how this can get sprayed up into the atmosphere, and so it affects there too. A lot of what happens on land does affect what happens in our atmosphere, such as pollution, how we treat our own planet, CFCs we're going to learn about today and how that affects the atmosphere, solar power, like we are super solar powered on this planet. We know that ash can affect stuff. We know that how warm it is can affect stuff. So there's a lot that is very dynamic about our planet, and it really integrates with each other. It's not just one thing's happening in the lithosphere and it's not affecting other things. It's not like something's happening on land and it's not affecting the ocean, or ocean isn't affecting the land, or either of those isn't affecting the atmosphere. Okay, so the atmosphere, if we had a sample of air, is gas. We've talked about this before. It's made up of oxygen, nitrogen, and helium, and that's what we breathe. Okay, we don't just breathe straight oxygen. We can't, actually. So for those of you who have ever experienced the oxygen bar that occasionally shows up on campus, you can't sit there and just sit at the oxygen bar all day. You actually have a time limit, and that's because too much oxygen is bad for us. Now, yes, we need to have certain levels of oxygen in our body, and breathing straight oxygen makes you feel kind of happy, but we can't do that consistently. However, the amount of nitrogen and helium that is in our air actually varies depending on where you are, because you'll have less or more, or depending on which layer of the atmosphere you're in, depends on how spread apart the gas molecules are. Another thing that affects the air we breathe is if you're a diver. So if you dive and you go really, really deep, like cave divers, you actually have to have a ratio mix of oxygen to nitrogen to helium. So when you're shallow diving, you have basically the air we breathe, but the deeper you go, the higher amounts of oxygen you want in the mix. So it's really cool. But basically, gas, okay? If we put it under tests, we would find that there are different responses to different triggers or different things, right? So it offers resistance to pressure or force. Have you ever tried to squeeze a balloon? The balloon just will pop eventually because that's the response to pressure. If you have a plunger in a bottle, okay? If you push down, or a French press, if you push down too hard in a French press, the liquid has a response, correct? Like you can shatter it. The same thing happens with air. If you have a tube that has no exit and you have a plunger and you push down, you'll feel resistance at some point and you can't push the plunger past a certain point. That is air resistance to pressure and force. Air is transparent on composition. The molecules are in motion. They're moving very quickly. They're not touching. It's a gas, okay? It's very thin. Most of the atmosphere, or 90% of the atmosphere, is in the first 10 miles, and half is below 3.5 miles, which is where we are. Okay. Gravity does impact the heaviest molecules of air. It brings it closer to us because it's heavier. It's going to come down. Horizontal changes don't make much of a difference in our atmosphere, but vertical changes are very significant. So as you move up in the atmospheric density and pressure changes, as in like you go up, it decreases. The average sea level pressure is 1,000 millibars or 14.7 psi. So that's at us. So the higher you go, have you ever heard the air gets thinner? Well, that's very true. The air does get thinner. There is less, and that partially has to do with gravity. And like I said, vertical changes are very significant. Okay, so increase in altitude means a decrease in pressure, which we see right here. Okay, so we have altitude and we have pressure. Okay, over here we have miles. And what we notice is that 50% of the atmosphere lies below right here, which is probably like 6 kilometers, 5.5, 6 kilometers. It's close to about 4 miles above sea level. Okay, so this 0 is sea level, which is where we are in Florida. Okay, and so we're going to see this curve in pressure. That as we go up in altitude, we start out with a curve, and then when we get about 16 kilometers or about 10 miles up, it really just starts to go straight at 0, where we have 0 pressure. So the air pressure at the top of Mount Everest. We've all heard of climbing Everest, correct? So if you are a person and you are standing at the top of Mount Everest, you probably can't breathe. A lot of people need air support when they're at the top of Everest. People will train for months in order to breathe at the top of Mount Everest because it's just so high. The air pressure is only about 314 millibars. Goodness. Okay. So at 5,000 feet, it's much easier to notice just at 5,000 feet. Okay. When you get to 10,000 feet, people tend to have something called altitude sickness, which is when you have slight of breath, like you have trouble breathing, like you have asthma. You have trouble sleeping because you're having trouble breathing, but it won't kill you. At 15,000 feet, you start needing to have oxygen with you. At 20,000 feet, you can freeze to death. A lot of people will freeze at Mount Everest. If you do not keep moving, you will freeze. At 20,000 feet is also where we have cruising altitude. That is where your plane drives by. 20,000 feet. It's very cold. Your cabin at 20,000 feet is pressured 80 to 85% to compensate for the vertical variation. The pressure difference also causes air to move. Air undergoes a lot of pressure, so high pressure in the atmosphere leads to weather being a specific way and low pressure another way. So high pressure leads to clear skies, no clouds, no rain. Sometimes you're going to have cooler weather, sometimes you have hot weather. But generally a high pressure area is kind of where you want to be because that's where you're like, oh, I'm not going to have a storm today. Great. It's going to be sunny. It's going to be wonderful. When you have low pressure areas, that's where you have storms and weather that's not so great. In the summer in Florida, we tend to have a lot of low pressure zones pop up because, well, it's Florida and it rains here a lot. But we do get a lot of thunderstorms. So thunderstorms are low pressure zones. Hurricanes, super low pressure zones. Tornadoes, another low pressure zone. Okay. So yeah, the higher you go, the less pressure there is, which means the less air there is for you to breathe. So let's go way up here. This is 102,800 feet. It's about 17 miles or close to probably 27 kilometers up in the air. Air pressure, 9.6 millibars. Gosh, megabytes. Millibars. You know what you probably can't do up there? Breathe. So yeah, even up here, you technically need a breathing apparatus. People will train to be able to breathe up there without any help, but there are a lot of people, if you look up photos, where they're on top of Mount Everest with a face mask on and they're breathing. In Hawaii, Mauna Loa, just going up Mauna Loa, you have an air pressure difference. To the point where if you have a bag of chips at the bottom of Mauna Loa and you go to the top, that bag of chips will pop. Because pressure difference. Oh, sorry. It decreases. And if you were to buy a full bag of chips, like air is full at the top of Mauna Loa, and go to the bottom, by the time you reach the bottom, that bag will pop because you have an increase in pressure versus going up, you have a decrease in pressure. So even that, and people can get air sickness up there. Denver, Colorado, the Mile High City. People have trouble there when they go there because they're not used to that. Maybe they'll have trouble breathing. If you're an asthmatic, you definitely have trouble breathing. So there's all these things that are influenced by air pressure, and it all has to do with just how high you are. So what is air? Okay, so we know that we breathe air. We know the majority of it is oxygen and nitrogen with a smidgen of helium. But there's more to air than just those three things. Air has a permanent group composition and a variable group. So it will remain constant up to about 80 kilometers in elevation. Carbon dioxide is a natural component of the atmosphere, and it occupies a small but important percentage of a volume of air, about 0.038%. Okay. Carbon dioxide enters the atmosphere not just through us in the form of pollution, such as the burning of fossil fuels, deforestation, but also through things that are normal, such as just breathing of animal life, volcanic eruptions, the natural decay of vegetation when it dies. Photos and removal happens naturally as well. Plants create photosynthesis. As I'm sure many of you have heard, the Amazon is the greatest producer of oxygen on the planet, although it is currently burning, or at least it was when I made this video. I'm hoping by now in November they have fixed this problem, but it was burning in August and probably late July, and it wasn't getting any media attention, and people are very upset about this because the Amazon, along with the rainforest in the Congo, are the biggest producers of oxygen on the planet because they're just so massive. So it is, and carbon dioxide, going back to that, is an important greenhouse gas. Okay? Because along with water vapor, it traps a portion of the energy leaving the Earth, which helps warm the planet. This causes, so if there's more water vapor and carbon dioxide in the atmosphere. So if you have a lot of water vapor and CO2, you're going to have an increase in temperature on the planet as well because it traps it. And this is why currently our average surface temperature is increasing because we have all these greenhouse gases. But we're going to get to that later. So not only the water vapor and carbon dioxide are not the only greenhouse gases. We also have methane, nitrous oxide, and chlorofluorocarbons, which are known as CFCs. Okay, these can contribute to global warming, which we, again, will learn more about later. But water vapor varies from place to place and from time to time and season to season. Okay, you'll have more water vapor, let's say, in the summer than you do in the winter, in the northern hemisphere, but the southern hemisphere, same thing. Okay, close to the surface and warm, steamy tropical locations can account for 4% of the atmosphere, whereas in colder Arctic areas, it may dwindle to a fraction of 4% of the atmosphere. So your longitude and latitude affects how much water vapor makes up your atmosphere. So water vapor is invisible and only becomes visible when it condenses into rain or snow. Ozone is the primary ingredient of photochemical smog. Okay, so you're all thinking smog. Isn't that the stuff that's in a city like Beijing, where you fly over Beijing and you look down and the clouds are black? You're thinking of city smog. So Beijing, yes. For those of you who don't know, currently China is working on efforts to reduce its output of pollutants. Okay, but yes, up to this point, so Beijing has what they call city rings. So the closer you live to the center of the city, the more pollution there is, and that's where you really get those images of people in China wearing those face masks of different varieties, because that's where you want to, because they also sell these face masks that are have these filters in them, and you have to replace them every so often. And when you do replace those filters, they come out black, and that's how much pollution is in the city of Beijing. It is so bad that the cloud cover over the inner rings of the city is black. So when you fly over it, you can tell where you are because the clouds are black. But on the outer rings, it's not as bad. You have clear skies and everything is fine. But this type of smog is very different, this photochemical smog. This smog will irritate your eyes and your throat. And it's damaging to vegetation. So city smog is also damaging, but this is a different type of damaging. We are actually allergic to ozone. So ozone is O2. Okay, we are allergic to this. This is deadly to us. We've all smelled it before. We know the smell of ozone. It's whenever there's a lightning strike, we will smell ozone. But yes, it is dangerous to us. It will irritate our eyes and throat, and it will hurt the vegetation around us. So it's not something that we want down here on the surface with us. We want it to stay up there in the sky because this is what's protecting us from UV radiation and other types of radiation. It's kind of like our first layer of sunblock, and now we need to put on other types of sunblock so this way we don't die when we go outside, right? Ozone is found primarily in the upper atmosphere, such as the stratosphere, which you don't really need to know. Where was I? Atmosphere, stratosphere. Oh, I'm sorry, it's not O2, it's O3. I take that back, O3. O2 is oxygen. Anyway, ozone. So O3, or ozone, is primarily found in the stratosphere. It forms naturally as oxygen atoms combine with oxygen molecules. So you'll have an O2 mixed with an O, and it gives you O3, which is ozone. So O3 is very important for us because, again, it protects us from UV radiation from the sun. It also protects us from microwave radiation and other types of cosmic radiation that we get from star clusters, etc. And we'll learn more about these other types of radiation in the last couple lectures when we talk about stars. But although it's very important for UV radiation, when it does protect us from UV radiation, it breaks back down into this O2 and O. Okay? And then at night when it's dark, it comes back together and reforms the ozone. And everything should be all fine and dandy, right? We shouldn't have any lessening of the atmosphere, except we do have this thinning of the atmosphere that's going on. We've all heard about the holes over the Arctic and the Antarctic. And we're going to talk about that in a second. But this is where that starts. It's because they have constant sunlight, so it makes it hard for them to constantly rebuild. But yes, so if we add UV radiation to the mix, it breaks down the O3 into O2 and O, and then at night it will go back together, right? Not really. So what's happening here is these CFCs, or these chlorofluorocarbons, they come from things like dust and soot, or aerosols. And so what this does is it causes a problem with our ozone. I'm sure you're wondering how. So we all know the word aerosol, right? We see them in spray cans, we see them in, or we used to see them in spray cans and hairspray cans and stuff like that. So now when you go to the store, you'll see it saying CFC free or aerosol free. But soot and such are also aerosols. Today we really use them as refrigerants and propellants for blowing plastic foam insulation and solvents for cleaning electronics, like the microcircuits, but they have an important effect on our atmosphere. So even though there's a small average concentration of CFCs, they can destroy the ozone by breaking down in the stratosphere and then releasing chlorine, causing ozone reduction in parts of the northern and southern hemispheres, resulting in these holes. So what happens is a CFC, or an aerosol, will combine with an oxygen. And they don't let go. They have, they just don't like letting go. They have issues. So they get into a relationship, and this is a very toxic relationship, but neither of them can give up the relationship, so they're stuck to each other. And so this relationship keeps going, and they keep staying bonded because one's not going to be the first one to give up, and anyway. So then you have all these other O2s just hanging around going like, hey, wait, we were in a relationship. We need to get back together. And the oxygen that's with the CFC is now like, well, now I can't. I'm with someone else. We're never getting back together. Or maybe the CFC says, nah, bro, they're mine now. But yeah, so these are our variable gases. CFC is a small concentration of the overall amount of greenhouse gases, but it is a very impactful one. So like I said, we have our permanent and our variable. So the composition of our atmosphere starts with permanent. Okay, so let's do permanent. So our permanent is oxygen at 20%, nitrogen, which is the majority at 78. I know, who knew? We breathe predominantly nitrogen. Argon, hydrogen, helium, and xenon. Xenon, yes. And then we have our variable gases, or the superglue. So we have carbon dioxide, which is normal, methane, which if you don't know what methane is, we fart it. CFCs, water vapor, ozone. I don't remember what methane is. And then we have nitrous oxide. So I'm just going to write farts, because I'm sure you will all remember if it says farts. All right, so, and this is what it really looks like. So if you put it in a big bubble, we really breathe majority nitrogen. It's not a joke. And so that kind of makes it fairly interesting for us because everybody's like, oh yes, we breathe air, and we all think oxygen. But in reality, we breathe mostly nitrogen. So we have multiple parts of our atmosphere. There are many layers. We have the troposphere, stratosphere, mesosphere, and thermosphere. Okay. So as you move up in the atmosphere, temperature will increase and decrease as the atmosphere thins, and this has to do with the chemistry of the 4 different layers. So the troposphere, which is where we live in the troposphere, you have a temperature decrease with increase. Okay, temperature decrease with increase. That means the higher you go, the colder it gets. So at 20,000 feet, okay, it's pretty cold. You can freeze. Remember, the top of Mount Everest is like 26,000 feet. Okay. This is not good for us. We don't want to be up that cold. We are getting down to like minus 40. Yeah, about minus 40 up here. That's pretty cold. Celsius and Fahrenheit. But then when we get up to the stratosphere, so the average environmental lapse rate is 6.5 Celsius per kilometer for the troposphere, and averages about 12 kilometers in height. The stratosphere is 12 to 50 kilometers. That's how big it is. Okay, up here, this is where the maximum ozone is. Okay, and most of it is in the stratosphere. After this, we don't have any more ozone protection. So in here, though, temperature increases with height. And then we get to the mesosphere. Mesosphere is 50 to 80 kilometers, and again, temperature decreases with height. And then we get to the thermosphere. So the thermosphere has no defined upper limit, meaning we're not really sure where that part ends. We know it's there, but it's very thin, so we're not quite sure where it leaves. This is where you're going to see the aurora borealis, and the other one, which happens in the south, but we care about the aurora borealis because that's what happens in our region, the northern hemisphere. And so this is only a fraction of atmospheric mass. Gases move at high speeds, and temperature increases, okay? So all these areas where we're having an increase in temperature, this is where our gases are moving super fast. And remember, speed generates heat, and so this is why this is happening. All right, so what goes on within our atmosphere? Well, we have weather. So we're going to see rain, formation of clouds. We're going to have sunlight, and so we're going to have energy and heat production. And there's a lot of things that come out of this. So clouds aren't just all at one layer. Clouds will form at varying layers. You have low, medium, and high clouds, and so some clouds only show up here. Some clouds kind of only show up here. Some just kind of show up here. And then there's ones that kind of like go through all of them, and that's our cumulonimbus clouds. That's our storm clouds. But sunlight comes through all of this. And this generates heat and energy. So energy is visual and infrared. And this is how we're going to get the greatest amount of energy. Like 88% of the energy that happens in our atmosphere is visual and infrared. UV energy is about 18% of the total energy. Okay, but we tend to feel that the most because we feel the heat. Well, no, that's infrared. We feel the heat. UV radiation is what gives us sunburn. So let's look at kinetic energy, right? We have wind. Wind is constant on our planet. That's why we have the Coriolis effect happening. If there was no wind, there would be no Coriolis effect. And so we'll see wind every day. We see it when we look at our windows and we see just the trees kind of moving a little bit. We see it when we see clouds going very quickly across the sky. That's upper atmospheric winds. Um, I don't have really any wind going on outside right now that I can see that you would be able to see in a camera. It's not happening. We have wind that happens because a storm is coming. We have wind that happens during a storm. We have wind that just is a gentle breeze. That's just normal movement. Breezes at the ocean or breezes at a lake. Breezes going on and offshore all happen because of this kinetic, well, technically it's due to solar radiation when it's over the ocean, but just saying. And then we have potential. So our potential energy is in the oceans, and it's often used in hurricanes. And we're going to actually get to this specific thing later when we get to weather extremes. So sun and solar radiation. This leads to light energy, light you can see, energy you can feel in the form of heat. And then we have other energy, including gamma, X-rays, UV, visible, infrared, microwave, radio. The ozone protects us from a lot of these, such as gamma, some UV, X-ray. We can see visible light. We can get microwaves in here. We get radio waves, but we don't see much on the level of X-rays, gamma rays, or anything to the bluer side of the spectra, which is kind of cool. So we're going to start with heat and temperature, parts of energy that we receive from the sun. So heat is synonymous with thermal energy, and we should all know thermal energy because I'm assuming we all have stoves, or have at least seen a stove. Thermal energy is what heats stuff. We create it sometimes through electricity or through gas, or just fire. And that's all thermal. You can feel the heat. It touches you. This is always transferred from a warmer to cooler object. Yeah, that means ice cubes are absorbing heat, not giving off cold. I know. Temperature is an intensity or degree, and it's raining. It's an intensity or degree of hotness. Okay, so it's not like, oh, the temperature's really high. It's just so much energy coming through. No, it's a degree of hotness in the air. Mechanisms of heat transfer include conduction, which involves molecular activity. And we should all understand conduction, so we should know, hey, this is hot because it's a conductive metal. If I touch it, I will get burned. Or we know that some metals conduct heat or transfer heat better than others. Okay, aluminum foil. Aluminum foil heats up and cools off fairly quickly. Okay, and then we have convection. So convection, we should all know so well from boiling water. So we're going to use a great example. So convection, you're going to have hot water rise. In the case, this is water. Heat source, container, right? And hot things always rise, like hot gas or hot liquid. So it's going to rise, and cold will always sink. And that is how conduction works, or convection works. It's not just liquids, it's not just gases, it's both. So as something heats up and it goes up, it forces the colder to come down. And this happens in our atmosphere itself, and it's part of why we get sea and land breezes. And then we have radiation. So radiation, we have electromagnetic, like UV, visible, infrared, X-ray, microwave, etc. And radiation is probably one of the scarier ones because we can't see radiation. This is part of the reasons that people get skin cancer, because we know we get burned from sunlight, but we can't see the radiation that's hurting us. When people get radiation therapy for Cancer. We don't see the radiation. It's not this big neon glowing thing like we have in cartoons. It's mostly invisible. X-rays, invisible. Okay? Um, you can die from them. Look at Marie Curie. Gamma radiation is probably one of the most dangerous forms of radiation next to UV, and yet we expose it to ourselves when we're trying to get rid of cancer cells. So it is a mechanism that can really hurt us. Remember, radiation burns. Don't forget that. Okay? Doesn't matter that you can't see it and you can't feel it. You get burned from it. And for those of you who may have watched Chernobyl, that was gamma radiation from a nuclear explosion. And that, if you saw, their faces were turning bright red. They were being burned. Okay? So it is a large amount of heat transfer. It is very dangerous. Always be aware. And then we have advection, which is movement of wind, and yes, that will move heat. And then we have the water thing, and we're going to go over that in a little bit. And so this is how all of this works. So we have solar radiation coming down, which will be absorbed into the surface, which then gets conducted up into the air, which goes into the atmosphere, and then we have convection. And then advection happens, where cold air will come in horizontally and swoop in and move heat along. So differential heating is a temperature imbalance, and the atmosphere will try to fix it always, using different energy transfer mechanisms like convection. And this is where the water thing comes into play that I said earlier. So specific heat is the amount of energy needed to raise the temperature of 1 gram of a substance 1 degree Celsius. And then we have to look at the ability of said substance to accept energy and its response to energy. So heat capacity is the amount of energy heat an object can store. So for example, sand cools very quickly. As soon as it gets dark, it lets go of all that heat. So it has a low heat capacity, whereas water has a high heat capacity. It takes a long time or a longer time for water to cool than land. So like aluminum foil, land heats and cools 5 times faster than water and basically the ocean, thanks to differential heating. And so like I said, this is the water thing that comes into play, where it's basically whether is energy transferal into the atmosphere. Okay, energy is transferred into moisture in the atmosphere, leading to rain or other things. So it's energy transfer. And we can kind of see that here, that depending on the month of the year and the temperature, you can see how hot or how cold it is based on where it is. So Winnipeg, which is in the middle of the continent, in the months of June, July, and August, it gets pretty hot. But it gets pretty cold throughout the rest of the year, whereas Vancouver has a more consistent temperature. It doesn't get as cold, even though it's a little bit north of Winnipeg, but because it's on the coast, it stays warmer all year long. So what factors influence temperature? So we have the primary factor, secondary factor, and tertiary. So primary factor is latitude. How much energy are you getting is based on how far north or how far south you are. And then you have longitude, which is your surface type or your geography. So are you near the water or are you in the middle of a continent, like Vancouver and Winnipeg? And then your elevation. How high are you? Are you at the top of Mount Everest, or are you in Florida, where you're of a very low elevation? Secondary is advection. So wind coming in and ocean currents, because ocean currents affect weather, which we learned in the oceans section. And then we have tertiary, such as local topography. Are you in a hilly area or a low valley area? And local characteristics such as cloud cover and albedo. And albedo has to do with your ability to absorb and reflect energy. So next, we're going to talk about solar radiation types, but we're going to start with some of the laws. So all objects emit radiant energy. Hotter objects will emit more total energy per unit than colder objects. Hotter objects radiate more shortwave wavelength radiation than cooler objects. And good absorbers of radiation are good emitters as well. And so there are actually names for these, such as Planck's law, Wien's law, and Stephen Boltzmann's law, but we're not really going to focus on the names as much as the laws themselves. You also don't need to look up the equations for them. If you are curious about them, go ahead and look them up. Stephen Boltzmann, Planck, and Wien's law. So solar radiation. It's a big deal here. Everything is solar powered, technically. So what happens when solar radiation reaches Earth? Well, a couple things can happen. It can be transmitted, which is what happens to most energy, where it goes through the atmosphere as light that we see. Absorption, some energy is absorbed into the atmosphere. We have reflection, where energy kind of comes in and then immediately turns around and leaves. And then scattering, where energy comes in and then just poof into variation of molecules. Just because of how they're oriented, they just scatter. And so this is essentially what it looks like. So here's our solar radiation. And so here we're going to have the transmission directly to the ground, where it can either be absorbed or reflected all over again. So here is about what they assume is about 5% gets reflected back into space. Okay, 5% goes back. Okay. 30% is initially lost to space by reflection and scattering. Okay, you're going to have 20% reflected due to clouds, and 20% will be absorbed by said clouds, and then sometimes, depending on how the molecules are made up, they'll just scatter. Okay, so that's backscatter versus reflection. So a cloud reflects, the molecules in the atmosphere itself will scatter. So the thicker the clouds, the more reflection you're going to get. The thinner the clouds, the less reflection you're going to get because of albedo. And so albedo is the ability to reflect or absorb. So a dark roof is going to absorb more. Same thing with asphalt. It's going to reflect less, whereas clouds, thick clouds have a higher albedo, so they'll reflect more. Okay? And this is scattering. So scattered light is due to just atmospheric particles, like it's kind of like a prism. It goes in and just scatters everywhere. So how much is absorbed or reflected? If the ground absorbs the energy, there is an increase in temperature. If it is reflected, nothing really happens. And this is measured by the albedo of the surface or its reflectivity. Example, snow versus a parking lot. So snow is going to have an I albedo, mostly because it's such a light color. It's white. So that means it reflects a lot of energy. This is why it doesn't really melt, especially when it's in other areas that have low albedos. Or, yes, high albedo. Okay, a parking lot is usually black. So it will absorb a lot, meaning it has a low albedo. So if you have snow on a parking lot, the snow will melt faster than a snow in an open field. And that's just because low albedo, you're going to have an absorption of a lot of energy, which raises the temperature. So land and sea have different albedos. They don't heat the same way. They don't release energy the same way. Ocean has a high albedo. It reflects a lot of energy because that's what water does. And that's why you have a higher chance of burning at the beach than you do just being out in a field. The land has a low albedo, so it absorbs and becomes a lot warmer a lot faster during the day. So the Earth has a tilt of about 23 degrees. We're going to get back to what I previously said next time when we actually talk more about how this affects breezes. 23-degree tilt, and we tilt away from the sun in winter. So the northern hemisphere tilts away, meaning in summer in the south, winter equinox, so sun hits half the Earth, mostly the southern part, and it's focused on the Tropic of Capricorn in the south, which means the North Pole area, like Alaska, will have days of complete darkness. But during the summer, we tilt in the northern hemisphere towards the sun. This means that the sun is more focused on the Tropic of Cancer, and the North Pole and Alaska will have days of continuous light, where the sun never completely sets. But in the spring and the fall, light hits more of the equator, and so it's more equal. So the amount of energy possible depends on the latitude, the atmosphere, and the season. Okay? Cool. So we also see on Earth a change in the angle of the sun as it hits us depending on where we are. So if you paid attention as a kid, especially, you would notice that their sun at noon actually changes based on what time of year it is. Okay, so this is the longest day. This would be June 21st to 22nd and 20th. And then we have the shortest, the vernal and autumnal equinoxes, so spring and fall, where it's kind of like halfway through. And then we have the shortest day of the year, which is December 20th to 23rd. And that's where it's going to actually be the lowest in the sky. And that's why our days are shorter in the winter and longer in the summer. So this has to do with the circle of illumination, or the area of light on Earth, changing with the seasons, which is kind of neat. So how do we measure this temperature? A big way is a thermometer. And this is usually done hourly due to energy hitting the Earth with constant changes, causing temperature to rise and fall all day. And this is why on your weather app you have a high of and a low of. So thermometers are generally filled with either mercury, alcohol, or glycol. Glycol is it's like an oily substance. So the layers of a thermometer, yes, there's layers, involve glass, air, and glass in order to insulate the liquid within. This way, that temperature is only taken from this bulb region. So the bulb is either entirely glass or metal. And the space above the bulb in the tube will have no air. Okay? No air at all. It's a vacuum. So Celsius made the standard system of 0 to 100 degrees to show freezing and boiling point because Fahrenheit is super random. Okay. Lord Fahrenheit calibrated the first thermometer with water, ice, and boiling. So 32 and like 200 or 312 or something like that. Celsius came in to make a standard system. And then came Kelvin, Lord Kelvin. And Kelvin was like, we need something better than this. And he comes in and gives us absolute zero, which is minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. It's a lot. So, like I said, we tend to use Celsius in science, especially when it comes to things on Earth. We use Kelvin when we talk about space. Okay? And there's a vacuum because we need to make sure temperature is only taken from the bulb, because otherwise it's just going to go all over the place and it won't work. So we have thermal variations on Earth because of these temperature changes. So during the day, you're going to have convection and advection, which mixes the atmosphere. So during the day, you have equalization, not a lot of variation. At night, Earth is cooling, leading to more variation. So you'll have it be more windy at night than it is during the day, especially by the ocean. If you have a calm night, you're going to have a lot of variation. If you have windy during the day, there's mixing and less thermal variation. And if it's calm during the day, you're going to have more thermal variation. If you think of it as layers, you will have physical thermal layers on Earth if it's calm, where each layer ends up being either hotter or cooler depending on where you are. So if it's windy, these striations don't occur. Instead, what you're going to get is mixtures because of wind happening. And then we have a difference between overcast and if it's cloudy. So if it's overcast, you're going to have the same thing versus cloudy. So overcast day, more variation, less sun, but you're going to have it a little muggy or humid. Night is going to give us less variation, but it will trap heat and it will cause it to become more humid. If it's cloudy, you're going to have more overcast, more variation during the day than overcast, and at night you'll have only some variation and it's hindered due to heat trapping. So temperature and pressure causes changes. So when temperature increases, your air density decreases and your pressure decreases. But when temperature decreases, everything else goes up. And this has to do with counterbalanced changing the volume of air. So there is a difference in behavior between warm and cold air. Warm air is low pressure, cold air is higher pressure. We also have this thing of, remember with water, cold is denser, hot is less dense. But this doesn't mean you have a high or low pressure system. You can have cold air with a high pressure system or warm air with a high pressure system and vice versa. So isopleths and contour lines are a way for us to actually talk about these. So a line will indicate equal value. So one side equals less and one side equals more. These lines will separate areas based on data like temperature and pressure. So an isotherm has to do with temperature because thermal pressure is an isobar. So an isopleth analysis is a method to spatially organize and summarize data into coherent patterns that may have physical relevance. These are organized by area and are generally temperature. Similarities in patterns, and these tend to actually match topography. You'll actually see bends in the isopleth because of topography changing things. So again, the types are isotherms, isodrotherms, which we're not going to talk about, and isobars. And here's what they look like. So we can see that they kind of create these squiggly lines based on, yeah, you guessed it, topography, because you make like a whole bunch of little dots and then you connect the dots based on their temperature or their pressure. So the closer the isotherm is, the quicker the change in temperature, and same thing with isopleths, pressure. And this is calculated by looking at the temperature difference and distance over distance. Okay, so temperature over distance. So let's say the distance, like right here, is 2,500 miles. Okay, we have 93 and 13. So we're going to do 93 minus 13 over 2,500. And this essentially gives you 0.032 degrees Fahrenheit per mile change. So that means as you're traveling north, every mile you go, you're going to have a 0.032 degree Fahrenheit difference. So global temperature patterns. These are important because temperatures decrease as you move from the tropics to the poles. Isotherms exhibit latitudinal shift with seasons. Warmest and coldest exist over land, and global temperature patterns exist as well. So in the southern hemisphere, isotherms are straighter and isotherms are more stable. Isotherms can show ocean currents as well, and they show annual temperature ranges because they're going to be small temperature ranges near the equator, and they will increase as you get closer to the poles. And they're going to be the greatest over continents rather than over the water. Water is actually going to have more straight, and it's going to be more representative of currents, which we can see here. We can see that these are generally straighter. Part of it is because there's less land in the southern hemisphere. Part of it has to do with how many mountains we have up here. There are a lot of mountains. And generally, yeah, a lot of land versus less land. So right here what we have is the difference. Last one was winter in the southern hemisphere. Now we have winter in the northern hemisphere, or summer in the northern hemisphere, winter in the northern hemisphere. So now it's summer. And we can see still greater variation than in the south, but we see that curves are a little bit different. Like instead of it being like this in the north, now we have these very great differences in temperature. So since we will be learning about it, what is weather and climate? So remember, weather, short period of time, constantly changing, studied by meteorologists versus an average of a long period of time being climate. So there are properties that are measured regularly, like temperature, humidity, type and amount of cloudiness, the type and amount of precipitation, air pressure, wind speed, and direction. These are all elements of both weather and climate. It is because of these weather measurements that climatology is able to exist. So within our atmosphere, there are parts called selective absorbers, or SAs. These are variable gases. They take in long-wave radiation, short-wave radiation, or both, and like water vapor, carbon dioxide, CH4, and ozone. The absorption of radiation is a natural result of atmospheric chemistry, but our addition of extra sources of these absorbers is what makes this more unnatural and creates what we call or enhances what we call the greenhouse effect. So greenhouse is something that tends to happen on its own, where it keeps us from essentially freezing, because the Earth is constantly giving off heat, constantly, and we kind of don't want to freeze to death. So by having some of these greenhouse gases naturally, it helps keep some of our heat in. But if we have too much greenhouse gases, it causes issues, such as too much heat being trapped. And we don't want to be Venus. So in a greenhouse radiation, all this stuff can come in. It either is absorbed and then sent back out as long wave radiation, where it's going to be blocked in some cases from going back out. So it reduces the amount of heat that is released out, which for the most part is good, except when it's not. So CFCs, we talked about it breaking up ozone. The O atom bonds with CFCs, doesn't let go, therefore ozone can't repair itself. Okay, it can't continue its natural cycle. This is where we start to get bad. Sorry, this is supposed to be O3. So when sunlight hits, the oxygens break apart. O atom will bond with a CFC, won't let go. Ozone can't reform. This is part of why we have holes forming. But when we get to the poles being thinner, that's partially due to constant sunlight, and then add CFCs in addition. So this leads to environmental issues, okay, such as acid rain. If it lands in lakes or rivers or large bodies, it will, if it's really acidic, kill fish and plants, but it will destroy vegetation. Sources for acid rain aren't just things that we pop up in the atmosphere, but volcanic eruptions can cause this too, because they will throw up ash, they will throw up carbon dioxide. So like I said, normal things. A volcanic eruption is normal, but when we add extra is when it's not. So we have this urban heat island, which are cities. Cities are places that are filled with a lot of black bodies, and black bodies are something that absorbs all forms and type of wavelengths, such as streets, sidewalks, buildings, stuff like that. So we make these little urban heat islands. Cities absorb and produce a lot of heat. That's why they're so hot in the summer. We also have global change, or climate, which can be caused by volcanic eruptions. Like ash will block UV radiation in the atmosphere. It will increase acidity. And then we have astronomical issues, which is just dust in the atmosphere that can block out the sun's rays, decreasing temperature. And this can happen from, I don't know, an asteroid. And then we have just natural astronomical dust that comes in as well, which we'll learn later, it causes natural reddening of space. So what is the human impact? CO2 levels are rising, and mostly because of industrialization of the past 200 years, where we have been burning fossil fuels, coal, natural gas, petroleum, and of course, deforestation, which is part of why we have natural forests and national parks in the United States. It's to help preserve. So industrialization has caused a lot of problems and lots of effects. So for example, when England went through its industrialization period, they had this white moth there was more white moths before the industrialization and more black moths after, and that was just because of how much soot ended up in the air because of coal burning. So the present carbon dioxide level is currently 30% higher than its highest level over the past 800,000 years. And the reason we know the highest level over the past 800,000 years is because of climatologists looking at things like ice cores and sedimentary deposits at the bottom of lakes, which remember said could record how much CO2 was around. And so this is essentially what about 800,000 years of carbon dioxide looked like. It was never higher than 300 ppms, or parts per million. In 2015, it was up to 400 parts per million. So if that explains. And this is just as we've been getting more and more and more industrialized as a world, not even just a country, a world. So important impacts of human-induced global warming is a rise in sea level. Why would there be a rise in sea level? Melting of the ice caps. There is enough ice locked away, we talked about earlier, to raise the sea level enough to essentially erase all of Florida and a lot of the east and west coasts of every major continent. We have shifts in large storm paths. Changes in precipitation and distribution of said precipitation, changes in occurrence of severe weather, like where it's impacting, stronger tropical storms, increasing. So, for example, hurricanes are getting stronger. Yes, we've had a lot more devastating levels of hurricanes in the past, like 10 years, than we have before. We have a stronger tropical, increasing frequency and intensity of heat waves and droughts. And then gradual environmental shifts. So, for example, up north, winter is coming later. So rather than having snow in December, we're having more or less snow in March and April when we shouldn't have snow anymore. And then instead of having spring, we're jumping right into summer. So, to help hit home what is going on, the Earth does have natural cycles of glacial periods and interglacial periods. Okay, glacial meaning we have glaciers that have come down and taken over a lot of the continent. Interglacial meaning the glacier has receded. So right now we are technically in an interglacial period. And in interglacial periods, it's going to be warmer, sea levels will be higher, and then in glacial periods, because a lot of water is locked up into glaciers, it's colder, and sea level has dropped. So our actual, where we are right now, we'd be farther from the coast if this was a glacial period. So where we are right now should be starting to dip. We should be entering a glacial period. But instead what's happening is the global temperature is instead rising rather than falling, which we, based on data, should be happening. And that is basically what we're talking about with global warming. All right, so that is the end of our lecture. If you have any questions, please go ahead and post them in the discussion post that I have online for you. Have a great week.